Today, I'm going to be talking about multi-TeV signals of baryogenesis in the Higgs Troika model. This is based off work done with my colleagues Human and Ian. We have here the reference to our preprint, and this is submitted currently to PRD going through review. To begin, I'm going to go over baryogenesis and the baryon asymmetry of the universe. From various cosmological observations, from CMB measurements, and measurements of BBN, in other words, different ratios of nucleon number densities, we have some observed value of the photon number density and baryon number density of the universe. And a more convenient parametrization, though, if we're talking about this in our purposes, is this number density of baryons to the entropy density of the universe, which is around 9 × 10⁻11. This is a number that is far bigger than what the standard model can generate by itself, which means that this observation of asymmetry between baryons and antibaryons leads naturally into discussion of BSM physics. So any physics beyond the standard model or even in the standard model has to violate 3 conditions known as the Sakharov conditions in order to be able to dynamically generate such a baryon asymmetry. The first condition is baryon number violation. Without some source of violation of baryon number, there won't be any generation of an asymmetry in either direction. The second one is C and CP violation. This is ensuring that there actually is some sort of difference between baryons and antibaryons in the model. And the third condition, there needs to be some sort of interactions out of thermal equilibrium. So in fulfilling these conditions, we need to talk about not only what the standard model cannot do, but also what it can do. And the first condition of baryon number violation actually does turn out to be something that the standard model can do by itself. Perturbatively, baryon number is a symmetry of the standard model, but it is an anomalous symmetry, which means there are non-perturbative violations. In particular, there are these non-perturbative sphaleron processes, these electroweak sphalerons, which are vacuum transitions, can change antileptons into baryons in 3 units at a time. So baryon number violation is actually already okay in the standard model. However, CP violation, even though it is present in the standard model in the CKM phase, is not large enough. So there's the CKM phase as the source of CP violation in the standard model. And there's also the PMNS phase, which is technically BSM because one could say the standard model prediction is massless neutrinos. So this is strictly speaking a BSM phase. These are both not generally large enough in order to produce the observed baryon number asymmetry of the universe. So this is something that new physics would have to accommodate. There needs to be new sources of CP violation in order to accommodate baryogenesis. For out of equilibrium dynamics, there's a few possibilities that are typically used. One of them is the decay of some heavy particles out of thermal equilibrium. This is used, for example, in leptogenesis scenarios where there are massive neutrinos which decay early in the universe. And these massive Majorana neutrinos specifically have lepton number violating decays. And then these lepton numbers can be converted into baryon number asymmetries through these sphaleron processes. The second typically used mechanism is a first order phase transition. And a lot of models try to accommodate this, specifically with the electroweak phase transition. It turns out in the standard model, the electroweak phase transition is not a first order transition, it's actually a crossover transition. But with new BSM physics in the Higgs sector, one can make the phase transition first order. And this is used, for example, in electroweak baryogenesis in order to generate the baryon asymmetry. So we are going to focus on this first scenario of heavy particles decaying out of thermal equilibrium. However, we are going to do it with changes to the scalar sector. And we're going to do this with our Higgs Troika model, which is 3 Higgs doublets designed to generate this baryon asymmetry. So in the standard model, there are 3 generations of fermions, but there is only this 1 Higgs doublet. And we are providing a sort of unification of this by saying there's also 3 Higgs doublets in this model. So we add in 2 heavy Higgs doublets, and the role of these heavy Higgs doublets will be to provide these decays in the early universe in order to get the out of equilibrium dynamics for baryogenesis. By adding in more doublets, we also have new sources of Yukawa couplings. These heavy doublets have Yukawa couplings to all the standard model fermions. And on the one hand, this gives us various flavor physics constraints. We have to make sure that we do not violate any flavor changing neutral current observations. And all of these provide very strong constraints on generic flavor structures. But on the other hand, we also have more potential CP violation sources from these Yukawa couplings. And also, even with the flavor physics constraints, an observation that right now may provide a constraint could in the future provide a discovery opportunity if violations of the standard model are discovered with more precision. So in order to complete the picture, we also add in 3 right-handed neutrinos so that we can accommodate Dirac neutrino masses in this model. So in this earlier paper of ours, we cover this general Troika framework in more details, but this is the general picture that we have 2 extra heavy doublets. Our general mechanism, since we have the decays of these heavy doublets providing the asymmetry, like in most of these sorts of baryogenesis scenarios, you look at the interference between a tree level diagram and a loop level diagram in order to get the asymmetry. So before electroweak symmetry breaking, we have a population of heavy Higgs doublets. We can say this is just generated by some heavy modulus field decaying into these doublets. And then the decays of these will be asymmetric between the final states of L bar nu right, the lepton doublets and right-handed neutrino singlets, and its conjugate process, the L nu bar right. And we can write a formula for the asymmetry of such a decay. We're going to choose to use H3 specifically for this decay. Just as a choice of which doublet to use, we say we're going to use H3. And the asymmetry here, on the one hand, we have a mass difference between the heavy scalars. This means that when there is near degenerate here, that this will be enhanced. And on the other hand, we also have the traces of various products of Yukawa couplings. So in the numerator, we have imaginary part of the product of 2 different traces. In the denominator, we have a product of the diagonals of the trace here. And in this particular diagram, we say we start with H3. So what is the role of H2? The role of H2 in this is to be a mediator in this. H1, since we were making H1 responsible for mass generation in this model, does not have sufficient Yukawa couplings, and it also acts as a light mediator for washout processes, which can destroy any generated asymmetry. For our choice of Yukawa coupling structure, in principle, we can just say the Higgs Troika framework can have arbitrary flavor structure, but we're choosing for this specific realization to base this off of the spontaneous flavor violating 2HDM based off work of our colleagues at Stony Brook. This is a general framework that gets rid of tree level flavor changing neutral current processes. And we're going to extend this a little bit. We're going to add in, on the one hand, we're adding in our right-handed neutrino singlets. And on the other hand, we're also adding in a second doublet, but we're giving the second doublet the same coupling structure. And the coupling structure in this spontaneous flavor violating model is that we have, on the one hand, up-type quarks, which have, for the heavy doublets, a coupling exactly proportional to the standard model up-type quark coupling. This means that these are proportional across all generations in the exact same form. We have a similar coupling structure for the charged leptons. It's proportional to the standard model coupling with some proportionality. However, the down-type quarks and our addition of the neutrinos have arbitrary couplings per generation given by these kappa D, kappa S, and kappa B for the down-type quarks, and kappa nu 1, kappa nu 2, kappa nu 3 for the neutrinos. We're doing this in the basis where the standard model couplings for these down-type quarks and neutrinos are also flavor diagonal. So the main thing of this is that each of these Yukawa matrices across H1, the standard model-like doublet, and H2 and H3 are simultaneously diagonalizable. And this gets rid of the tree-level flavor-changing neutral current interactions. And in particular, just to emphasize where the PMNS and CKM matrix come in, they are present in these standard model Yukawa coupling matrices here. For leptons is where the PMNS is, and the CKM is here for the up-type quarks, and it shows up in the exact same way for the H2 and H3 couplings as it does for the H1 standard model Higgs doublet coupling. And in this model, again, we're making that H1 is the source of all the mass generation in this model, including the Dirac neutrino masses. And for flavor physics purposes, to avoid introducing too many additional CP violating sources for flavor physics, we're putting all the new CP phases in the neutrino sector. So even with removing the tree level flavor changing neutral currents, there are still various loop level induced processes, and the observations of flavor physics for various things like neutral meson mixings and the flavor changing decays of quarks provide constraints for this sort of model. So we have here some plots here. We're choosing this C, this proportionality for the up-type quark coupling to be 1 for these plots. On the left, we're setting kappa S and kappa B, the strange and bottom couplings, to 0. On the right, we're setting these to be equal to the kappa D. And we have the upper limits from various observations here. The blue solid line in particular is the strongest. This comes from D meson mixing. We also have, however, B to D gamma decays here and kaon mixing showing up in this plot. On the right-hand side, we have the same ones here, but also now we have also B to S gamma showing up once we turn on this kappa S. Still, though, even for this scenario, for most of the mass range, the D meson mixing provides the strongest constraints. And for this purpose, we're also assuming that the two heavy Higgses have the same mass with no degeneracy in this case. To simplify the calculation, the picture isn't too much different if the mass degeneracy is still small. And if we look at a slightly different scenario where we have a smaller value for this C, we choose C here, C equals 0.1. A lot of these flavor physics bounds weaken, but the demixing is basically sensitive only to the kappas for as long as the C is small. So the D meson mixing bounds are still the strongest here for these two scenarios. The kaon mixing is also the same strength, but it is weaker than the D meson mixing for the mass ranges we're looking at. And B to S gamma is still present, but it's still weaker than the D meson mixing bounds. So on the one hand, D meson mixing is a current bound, but is also potentially, with future improvements, maybe a potential discovery channel for this sort of model. And now at a 100 TeV collider, we can look at the discovery reach as well as the region of successful baryogenesis in this model. So here we have similar flavor plots here. On the left, we're turning on just kappa D. On the right, we're turning on all of the kappas with equal strength. And we have here, again, the mass of the heavy quarks here, or sorry, the masses of the heavy Higgs doublets here. We're choosing, again, the C equals 1 scenario, which is basically a top coupling of 1. And we have here in the shaded regions, this is the region for successful baryogenesis given certain levels of mass degeneracy. So here for this C equals 1, successful baryogenesis requires masses of around 16 TeV or greater with 5% mass degeneracy. And we have here this dotted region is the flavor physics bound from the previous slides here. This is D meson mixing again. This is a mix of D meson mixing and B to D gamma on the lower mass region here. And we have curves here for dijet discovery reach at 100 TeV with 2 different integrated luminosities. And we have TT bar discovery reach for the integrated luminosities at 100 TeV in the same sort of way here. So for lower mass region, for lower mass Higgses here, the di-top final state could actually be stronger for discovery purposes. It can reach to lower sensitivity for the kappas. And there's also here on this plot here, existing existing experimental limits from ATLAS and CMS for the dijet final state. But these bounds right now for this particular model are already ruled out. This parameter region is already ruled out just by the flavor physics of this particular model. We have here a similar plot. This is for a lower value of C as before, choosing C equals 0.1, which is basically then a top coupling of 0.1. Now the di-top final state doesn't have as much discovery reach here. So we mostly focus on the dijets for this case here. So now we have dijets, the curves are somewhat similar, and the flavor bounds are also pretty similar here. But the main thing that's different now is we get much lower in successful baryogenesis for our mass reach. We now have successful baryogenesis as low as around 5 TeV. And here we have the similar plot, this time with the value of C equals 0.01. The main difference here is we get even lower in mass for successful baryogenesis. We now have just a couple of TeV, we can get the correct baryogenesis. The main difference for all of these 3 slides here, between the left and the right, is that for the right side here, the flavor bounds already rule out some of the discovery region for dijets. So these dijet channels could potentially see something, but it wouldn't fit in with the flavor physics of our particular choice of model here. So in conclusion, we have a 3 Higgs doublet model, our Higgs Troika, which can generate the baryon asymmetry of the universe. And this is a model that involves changing the scalar sector of the standard model, but it does not involve a first order phase transition. So this is a distinct sort of scenario from baryogenesis, where it involves a first order phase transition. Instead, we're doing this with a leptogenesis style heavy decay scenario. So a high energy hadron collider, particularly 100 TeV, has a chance to directly observe the heavy Higgses for this sort of model. But there's also the orthogonal discovery channels from flavor physics, particularly D-meson mixing, which if improved in the future, either experimentally or theoretically, can provide additional discovery avenues for this model. Thank you.